this is going. Even my very short list is spanning a dozen lines already, and that's only a very selected subset of all of the papers that have been written on these channels. But if you consider this isolated binary evolution, it goes something like this. So in stage A, you have two stars, 0H main sequence. The stars are pretty far apart. They might be a few astronomical units apart. Stage B, one of the stars, the more massive one, the primary, which is evolving quicker, expands. It starts transferring some mass onto the companion because the companion is exerting a tidal pull on the primary star. The star does what's called overflowing its Roche lobe, so it's transferring some mass onto the companion. It leaves behind a star which by now has had its hydrogen envelope removed, so it's a helium star, a Wolf-Rayet star. The companion, and eventually that Wolf-Rayet star goes until the end of its evolution and collapses into a neutron star or a black hole. Meanwhile, the companion, the secondary, also ages, also approaches the end of the main sequence, also begins to expand and transfer mass onto the now compact object next to it, the neutron star or the black hole, except in this case, we think it goes through something called the common envelope phase. So instead of dynamically stable mass transfer, we think the mass transfer, at least in some cases, is dynamically unstable. So what that means is that as the secondary star gets larger and fills its Roche lobe and starts to transfer mass, the radius of the Hill sphere around it, of the radius of its Roche lobe, actually shrinks faster than the radius of the star is able to shrink. So the more the star overflows the Roche lobe, the more it wants to overflow the Roche lobe even further. And this is a runaway process until at some point there is a big envelope of gas around the entire binary, which is now composed of the core of the secondary star and the compact object orbiting around it. This envelope loses co-rotation with the binary, in which case there is obviously significant drag. So you can think of this as regular Bondi-Hoyle drag on both the companion and the core of the secondary. And essentially, this drag takes energy out of the orbit, shrinking the orbit, and it puts it into the envelope, heating the envelope, allowing the envelope to expand, and ultimately, at least in some cases, expelling the envelope altogether. And so what's left at the end of the story is that the core of the secondary and the compact object actually come closer together by a couple of orders of magnitude. Meanwhile, the envelope is expelled. And so what you have now is a compact object, a very compact Wolf-Rayet star, say a solar radius in size, in a binary which is only maybe 10 solar radii in separation, which is exactly what you want to form a double compact object. And when the secondary explodes in a supernova or collapses in a supernova, it forms a second compact object. And now you just patiently wait for a few 100 million or a few billion years for gravitational waves to do the dirty work of bringing this object to merger. And lo and behold, LIGO, Virgo, Indigo, etc. can go on and detect their gravitational wave signal. The second solution. So the second solution is something that was independently but nearly simultaneously proposed by Selma Domink and myself, as well as a team led by Pablo Marchand. And the idea is basically the following. If stars rotate very rapidly, the rapid rotation can lead to enhanced mixing. One way to think about this is that under very rapid rotation, we're talking about a non-negligible fraction of breakup. The temperature on the equator and the temperature on the pole is different. And so you end up having meridional circulation or Eddington-Sweet circulation in these stars. And the circulation leads to enhanced mixing. And then enhanced mixing can bring hydrogen from the outside into the core and take hydrogen fusion products, namely helium, back outside towards the surface of the star. And the star, therefore, instead of developing the usual core envelope structure, evolves nearly chemically homogeneously. So you have a similar composition throughout the star that allows the star to fuse not just the central regions, but almost all of the hydrogen in the star into helium. And so at the end of the evolution, at the end of the main sequence, you just end up with a naked helium star, which therefore means the star, as it evolves on the Hertzsprung-Russell diagram, instead of becoming big and red, it becomes small and blue. It's very hot, very luminous, and very small in radius. So that means that at the end, this is the magic wand. But you might say, but what makes the star rotate so rapidly in the first place? Well, this is the beautiful thing. It's the very fact of the binary being so close that does the trick. Because if the binary is close enough, tidal forces are significant, and tidal forces ensure tidal locking, which means that the binary has both stars rotate around their axis at the same frequency as the angular frequency of the rotation of the binary as a whole, right? So the rotational period of each star is equal to the binary's orbital period. And that turns out for massive stars, especially massive stars of relatively low metallicity, to be high enough that the star can efficiently mix, and therefore this channel of chemically homogeneous evolution might work for sufficiently massive stars at sufficiently low metallicities. The next channel is dynamical formation. So this is the channel that Shurov, among others, has contributed to, and it might work in a few different places. It might work in stellar clusters, in globular clusters, in nuclear clusters, in AGN disks. The basic idea is anywhere where you have a dense stellar environment, you are potentially in a situation where you can have many body interactions. A three-body interaction involving a couple of three different objects can be enough to form a binary, even if the three objects were initially unbound. Once you have a binary, if it's a tight binary, or if it's a hard binary, meaning that typically the orbital velocity is larger than the typical velocity dispersion among the surrounding stars, or the orbital energy is larger relative to the typical kinetic energy of the surrounding stars, then future interactions with other objects will only harden the binary further. So an interloper will be ejected with an even higher velocity than it came in with, taking a bit more energy out of the binary, allowing the binary to gradually shrink over time until it shrinks enough that it can merge through the emission of gravitational waves. And this is another possible channel for binary black holes to merge. By the way, I should stop for a moment and ask, do people have any questions? Because if you do, please do feel free to ask. I'm very happy to stop and entertain questions. We don't have to wait until the end.
Ilya, you can continue. No questions so far.
Okay, thanks, Shurov. Okay, so now why do I have a dinosaur? Okay, yes, I do have some interest in paleontology, but I didn't get completely confused. I do remember what I'm supposed to talk about. So the reason for this dinosaur is that, you know, we never really get to see dinosaurs, right? Yet we know quite a bit about them. How do we know something about them? Well, we know about them because dinosaurs leave behind fossils. And a knowledgeable paleontologist can look at the fossil and can reconstruct from that fossil what the dinosaur might have looked like. So we want to do something similar. So this COMPASS project that Shurov mentioned in the introduction is an effort to try to solve the inverse problem of gravitational wave astrophysics. So what I would like to do, and many of my collaborators would like to do, is to use gravitational wave observations as a tool to better understand stellar evolution and binary evolution and dynamics. In other words, to go from a population of merging black holes, which are stellar remnants, kind of in the same way that fossils are remnants of dinosaurs, in order to understand some of the big key questions that we don't fully understand about stellar and binary evolution, like the physics of the common envelope phase, like the kinds of supernova kicks that black holes get, like the stability of mass transfer and the typical amount of angular momentum lost during non-conservative mass transfer, and so on and so forth. So there are all these questions in this picture of binary evolution, and we might be able to use the final part of the story, which is the properties, the rates, and the properties of the merging compact object binaries to learn something about how stars and how binaries evolved. So I've already gone through this picture of isolated binary evolution, but again, just to highlight the story, here is a plot from one of my former students, Alejandro Vino Gomez, made in a slightly different way. But again, we have two stars. One of them expands, overflows the Roche lobe. There may be a supernova. There may be a common envelope phase. But one thing I want to highlight here is this step on the third from the right step on the bottom line, which here is called KSBB Roche lobe overflow. So what does that mean? Well, it actually means that after you already have a compact object and a helium star next to it, in some cases, the helium star also expands at the end of its helium main sequence. It kind of does the same thing that a hydrogen star, hydrogen fusing star does at the end of the normal hydrogen main sequence. It develops, in this case, a carbon-oxygen core and a helium envelope. And as the carbon-oxygen core begins to contract, the helium envelope expands, and it might expand enough to actually cause another episode of mass transfer and Roche lobe overflow. So one of the interesting questions is this mass transfer dynamically stable or not? And this is the kind of question that we can try to address with population synthesis, with simulations of many, many thousands of binaries where we take, this is what we do with COMPAS, we use simplified recipes to evolve loads of binaries and then compare the predictions, the properties and the distributions of the observed population against observations to learn whether or not we got the physics right in our simulations. So let me actually skip a couple of things. Hold on, what's going on here? Somehow, okay, this didn't quite go according to plan. All right, never mind. Well, in the interest of time, I'm actually going to skip a few of these slides anyway. But the kinds of predictions we might make are predictions, for example, about the spins of the merging binary black holes. So these are predictions, some work by Simone Bavera and Tassos Fragos and some of the members of the COMPAS team. Here are some of the, again, some of the members of the COMPAS team. This is work led by Will Farr, where we looked at the few initial observations that LIGO made, and focusing in particular the spins of the black holes, and arguing that at least at that time the spins were inconsistent with, and that's still true, with being both high in magnitude and predominantly aligned. So that meant that there were two possibilities. Either the spins were, if they were high, they had to be relatively isotropically distributed in terms of their orientation, not aligned with the orbital angular momentum. That would point to dynamical formation. Or they could be just small, which I think is actually more likely, at least for the spin of the primary, because very likely the envelope contains the bulk of the angular momentum, and once you remove the envelope, there isn't all that much spin, all that much angular momentum left in the star, so the black hole will be born slowly spinning, at least in this context of isolated binary evolution. Now, the secondary, sometimes you can spin up a little bit through tides, and that's why you may have non-zero spins aligned with the orbital angular momentum, but most likely they will not be very large spins, and that seems to be consistent with most of the observations to date. The story of the KSBB mass transfer, I'm actually showing here. So these are some simulations, again, by Alejandro. On the left, we did the naive simple thing where we treated KSBB mass transfer in the same way that we treat normal mass transfer. And that turned out to mean that within our models, it was mostly dynamically unstable, leading to another common envelope phase. And so we plotted the simulated period eccentricity distribution of double neutron stars and compared it against the observed galactic double neutron star population shown in these purple diamonds. And as you can see, it's not a great match. And then we thought about it for a moment and we said, well, what if they really, this KSBB mass transfer was dynamically stable? Oh, look, then actually seems to be a much better match to the observed population, as you can see on the right. So it must mean that it should be stable. And after we've done that, we learned that some other people that had already done some of this work, we just didn't know about it, but Thomas Taurus and collaborators had argued using some detailed simulations, specifically of KSBB mass transfer, that it actually should be dynamically stable. So this was a way in which we were fortunate that we really could prove in this case that we could learn something from this population synthesis modeling. Now, in this case, we learned something that was already known, so maybe it wasn't that revolutionary, but it was still fun to figure out something through pop synthesis
what
modeling
problem?
and comparing. I'm sorry? So was
no,
that a question?
Go ahead, Ilya. Go ahead. I think it's
okay. And so this was really an opportunity to compare population synthesis models against observations and learn something from them. Other examples include working on luminous red nova. In the interest of time, I'm not going to discuss that, but suffice it to say that we think that luminous red nova are outcomes of common envelope evolution, and LSST in particular in the next few years may be able to observe hundreds, if not thousands, of these events, which might allow us to use their properties to constrain the uncertain common envelope physics. Mergers inside a common envelope. Yes, please.
So I think that there is a question about the color coding. I think this is a couple of slides before. Yeah, this one. What is the color coding?
Yeah, so sorry, I didn't explain the color coding. It's not that important here, but the color coding is that the things which are in orange go through a normal common envelope. The things which are in yellow go through what's called a double core common envelope. So when two stars have roughly comparable masses, they can both be on the giant phase at the same time. And in that case, you actually have a phase where really it's a joint envelope of both stars that becomes the common envelope, and both stellar cores are orbiting inside the same common envelope, and then might simultaneously inject both stellar envelopes. The objects in blue are actually objects which never go through through a common envelope phase at all, so they end up making very wide binaries. Most of them get disrupted by supernova, but a few might survive, but they make such wide binaries that they would never merge within the age of the universe through gravitational wave emission. Does that answer the question?
Yeah.
Okay. So just to mention a few other things which I'm not going to have time to talk about. So just briefly mentioning a few of them. So one very interesting thing is that sometimes you do get mergers inside a common envelope. And when that happens, you fail to eject the envelope, the black hole companion, let's say, spirals in all the way to the core. When it does it, it tidally disrupts the core and releases the binding energy of the core on a time scale that's very short. The dynamical time scale of the core is only a few hundred seconds. So that's sort of like exploding a big bomb inside a star. And you might imagine that probably looks a whole lot like a supernova, because that's what a supernova does. And it really does look a lot like a supernova, except it's actually an unusually bright supernova, we think, because what we think happens is that the previous in-spiral through the common envelope has puffed out the envelope and actually primed it to be much more efficient at converting the energy of the explosion into observable luminosity. And that means that these might in fact explain some fraction at least of superluminous supernova. So this is something that Sophie Schroeder, Morgan McLeod, Avi Loeb, and I argued in a paper from, I guess actually from this year, maybe last year, I can't remember anymore. Other interesting observations that are not directly gravitational wave observations include but are interesting again in shedding light on black holes are observations of microlensing. So here, this is some work that Łukasz Wojciechowski from the OGLE team and I did last year, where we looked at microlensing events observed by OGLE. So the idea here is you have some stars sitting in the galactic bulge, and you have a telescope that's staring at them over 30 years. Pretty boring, but at least the stars are big and bright, so you don't need to a particularly sensitive telescope, and you can just afford to have a pretty low sensitivity telescope staring at the stars for 30 years in a row. And once in a while, the stars tend to brighten for a bit. So if you look at the top left picture here, you see the light curve, and you see that there's a bit of brightening, right? So this particular star had a typical apparent magnitude of 15.6 or 15.8, and then it sort of temporarily brightens to about 14.8. Now, 30 years of observing the star never did this. Does this all of a sudden? What do we think happened? Well, the shape of the light curve is such that it seems pretty clear that it was actually a microlensing event, because some other object must have transited, must have moved pretty much in front of the star and bent the light from the star in such a way that a greater fraction of the starlight than usual was collected by the OGLE telescope. But in some cases, that lens itself is perfectly visible. You just see a star moving along, and it's blending its light with the light of the lens, and so the lens is blending its light with the light of the source. And okay, that's all well, good and clear. But sometimes you don't see the object that's doing the lensing, and yet from the shape of the light curve, you can infer that it must be a fairly massive lens, perhaps a few solar masses, up to 10 solar masses in mass. There is no way you would miss such a star. The only possible explanation is it must have been a black hole or a neutron star. And so therefore, you can actually study the properties of neutron stars and black holes in this way. And in fact, Łukasz and I had argued in this paper that microlensing observations tell us that there is no gap between neutron star masses and black hole masses, even though the most massive neutron star we know is just a shade over 2 solar masses. And the lowest mass black holes we had seen previously from observations of X-ray binaries weighed in at only about 4.5 or 5 solar masses. We argued there cannot be a mass, there should not be a mass gap. And in fact, interestingly enough, after this paper was already written, there was an observation coming from LIGO of a very interesting source where one of the companions was a compact object with a mass of about 2.6 or 2.7 solar masses, meaning that yes, objects in the mass gap really do exist. LIGO has confirmed this, and that's consistent with these observations we were making through a completely different data set. So the point of the story is, it's not just gravitational wave observations, it's also really a whole slew of other observations across the electromagnetic spectrum. I'm going to skip a few slides in the interest of time, so I'm not going to talk about other observations or models of common envelope evolution or other observational constraints, beyond just saying that the ultimate goal here, the ultimate aim, is to have a self-consistent story where we create a concordance model of stellar and binary evolution on the basis of a multitude of observations coming from both gravitational waves and the electromagnetic spectrum. But I was going to have this be my last slide, and then it occurred to me that we started with a bet, so we should probably finish with a bet. And since I got this invitation from Shurov, it was fitting that here's a bet that we were making with Shurov and Chris Blachinsky, Daniel Holtz, and Carl Rodriguez. This happened in Aspen, and here we are signing off on the bet. And here's the bet. So the bet was about whether or not black holes should exist in the mass range between 55 and 130 solar masses. Now, that was an interesting bet because there are models of stellar evolution which suggest that single stars should never make black holes in that range, because single stars in a particular range of helium core masses will get hot enough, about 10 to the 9 degrees Kelvin, that the photons, which provide the bulk of the radiation pressure supporting the star, will spontaneously produce positrons and electrons. In the process, the radiation pressure is going to drop, and that's going to lead to a sudden contraction in the star. And that sudden contraction increases the temperature even further, leading to explosive oxygen burning and an explosion of the entire star, leaving no remnant behind. Meanwhile, Karl and Shurov and a few other collaborators thought that there's a way around this story, which is that if you form and merge black holes dynamically, then you can hierarchically build up the mass. So maybe you merge two 30 solar mass black holes and you make a 60 solar mass black hole, and then you merge that with the 30 solar mass black hole and you make a 90 solar mass black hole, and then you merge that with another 30 solar mass black hole, and there you go, you have a merger of two black holes, one of which is in this pair instability supernova mass gap. And so they bet that at least one of the first 100 gravitational wave detections would be inside this mass gap. Now a couple of people, Stan Woosley and Fred Razio, later joined this bet. And here was a very recently announced, just a couple of weeks ago, detection, GW 190521. So you see here the plots. These are from the LIGO Virgo discovery paper, showing just the last few cycles that were detected, the ring down, quasi-normal ringing of the newly formed massive black hole. And from the frequency of these, you can figure out that the mass has to be very high because the frequency is inversely proportional to the mass. And in fact, here are the mass estimates you see on the bottom right. It really seems that the masses are in the mass gap, possibly for both objects, almost certainly for at least one of the objects. So it was my pleasure as the arbiter of this bet to award the winning of the bet to Shurov and his teammates on this particular bet. And also, of course, it was a great pleasure to see this bet resolved and this very interesting event detected. And we can probably have a whole other seminar just on this one event, because it's so interesting in so many different ways. But let me add with the story that this isn't by any means the last bet. There are many more bets along the way. Like here is, for example, a still unresolved bet about whether we will detect genuinely eccentric binaries with gravitational waves, because those would be very telltale signs of dynamical formation. The eccentricity for isolated binaries should decay to zero or very near zero long before they get to be in the LIGO band. And so hopefully with the aid of a few judicious bets, we can continue exploring the mysteries of stellar and binary evolution with gravitational wave astrophysics. Thank you.
Great. Thanks for this excellent talk. Let's thank Ilya. I'll just clap myself and imagine others clapping. All right. We will do some questions now, and I will ask the participants. Let's try it this way. If you have questions, please raise your hand, and I will call you one by one. I think Reshmi Lakshmi has a question. She actually typed it, but I will allow her to ask the question directly.
Hello. Thanks, Ilya. Can you hear me?
Yes, I can.
Yeah. You were mentioning about the 2.6 solar mass object. I was just wondering whether it is indeed a black hole, or if it is so, can it be evolved through single stellar evolution, or is there some other exotic models for that?
Right. So what we know is the object had to be very compact, because if it was not very compact, it would have been tidally disrupted by the gravitational field of its companion before the merger happened, and that would terminate the gravitational wave signal. So we know that it had to be compact. What we don't know is whether it was a neutron star or a black hole, because a neutron star, if neutron stars of that mass can exist, they're also going to be compact enough to have survived that particular spiral and to basically go through the event horizon of the black hole companion unscathed. The short answer is we don't know whether it was a neutron star or a black hole. Now, could you actually do this through isolated stellar evolution, for example, make an object of that size? We think the answer is yes. So Bernard Mueller is a colleague of mine who does detailed supernova modeling, and we wrote a paper earlier this year, unrelated to this particular event, but where we argued that supernova model predictions should generically predict that there ought to be stars that end up with leave behind remnants with masses in the mass gap. As I mentioned earlier, I think that's consistent with other observations, such as the microlensing observations. But in principle, and so I personally, my personal belief is that this actually is a black hole in the mass gap, in the previously construed mass gap, and the mass gap is an artificial thing. The mass gap was really due to the fact that for other unrelated reasons in X-ray binaries, it's hard to form and detect observable X-ray binaries with black hole masses in that range. But there is no real mass gap, that there are 2.5, 3.5 solar mass black holes. But I think we will need to see we'll need to wait for more data to be able to really confirm whether or not this was a black hole or a neutron star.
Thanks.
All right, let's give preference to students. Ambrish, you want to ask a question?
Yeah, hello, can you hear me?
Yes, I can.
Yeah, so first of all, thanks for the very interesting talk. And this question is about the double common envelope evolution that you mentioned, that when two stars of very similar masses evolve together and they both enter fill their Roche lobe together and enter a double common envelope phase. So how is that? Because both the stars are filling their respective Roche lobes, that means their envelopes are actually touching each other. So what's the difference between this scenario and the merging of two stars?
Right. Okay. So in general, unless you really fine tune things, it's not going to be the case that both stars overfill the Roche lobe simultaneously. Usually, it will be one star that overflows the Roche lobe first, initiating the mass transfer, and but the second star in this case, if it's already evolved enough, if it's already post main sequence and has a well-developed core envelope structure, then once this evolution inside a common envelope begins, it basically donates its envelope, contributes its envelope to the total envelope as well. Now, you're right that in a sense, this is, I was a little bit cheeky in my earlier statement that if stars just touch, they merge, right? That's indeed, common envelope phases are stars touching, and they don't always merge, because in some cases, the argument is that the injection of energy is able to, injection of energy from the gradual coming together of the cores or the compact objects is able to put enough energy into the envelope that you can unbind the envelope, but leave the cores behind far enough apart that they still survive intact. So yes, you're right to catch me on this. I was a little bit cheeky in saying that if stars touch, they just merge. What really we think happens is the merger is only inevitable if a star overflows its so-called second Lagrange point, the L2 point, because then co-rotation is really impossible, and then there is probably a fairly rapid onset of a merger. But otherwise, and that star was, let's say, a main sequence star at that point, so it doesn't have a clean core envelope separation. But if there's a clean core envelope separation in the star, then even with the loss of coordination, it's possible to, in some cases, to eject the envelope.
Yeah, okay, thanks. Thank you.
Anindo?
Hi, can you hear me?
I can.
Yeah, thanks for this nice talk. Actually, my question is like if we detect a binary black hole merger signal, from that, how can you distinguish between different source channels like common envelope, or it is coming from chemically homogeneous channel or dynamical channels?
That's a very good point. And unfortunately, we often cannot distinguish the source channel from an individual binary. Now, there are some things which can be useful signatures of one channel or another. So, for example, the chemically homogeneous evolution channel is, we don't think it operates in relatively low mass stars. We think it only operates in really, really massive stars. And so if you have a relatively low mass binary black hole or a binary neutron star, it probably didn't come from the channel. Another example is if you have significantly misaligned spins. So the spins are not aligned with the orbital angular momentum. Now we think that if there's mass transfer in a binary, then most likely that mass transfer leads to a realignment of the stars. And of course, there can still be a misalignment because if there's a natal kick during a supernova, that effectively tilts the orbital plane, so they can lead to some misalignment, but at least preferentially, we expect to see a relatively good alignment in those systems. Whereas dynamical formation, there is no reason to expect preferential alignment. In fact, naively, you would expect a isotropic distribution of the spin directions. Another telltale sign might be eccentricity. As I mentioned earlier, if you see eccentricity in the LIGO band, dynamics of some sort almost certainly played a role, because isolated binary evolution, you tend to form the binaries relatively wide, and then it's the eccentricity will decay. Basically, gravitational emission circularizes the binary quite efficiently, and so by the time the binary is in the LIGO band, it's circular. So that's all true for individual sources, but what we really want to do is look at populations, and as long as we can make robust predictions for the population properties, such as not just the individual spins and individual masses of particular systems, there, we can always argue, well, my favorite channel can explain this binary, but so can Shurav's favorite channel, and so can Chris's favorite channel, and so on. Instead, if we make predictions for our favorite channels in terms of the population properties, and then say which of these match the observed population properties, then we can really start talking about which channels dominate. Although it's also very possible that there is no single channel that dominates, that multiple channels contribute and multiple channels are important. It's worth keeping in mind that gamma ray bursts, for example, you have both short gamma ray bursts, which we think come from binary neutron star mergers, and long gamma ray bursts, which are a totally different channel that come from the collapse of very massive, rapidly rotating stars, and somehow their rates are roughly comparable. We think that type 1a supernova are completely different from the core collapse supernova, the type 1 BCs, the type 2s. The type 1a supernova probably come from either a single degenerate or double degenerate channel, but in either case, it's accretion onto a white dwarf, something very different from the collapse of a iron core in a very massive star. And yet again, the rates are roughly comparable. So it wouldn't be completely crazy to expect that nature is fond of playing tricks, and maybe some of these channels actually are competitive, and all of them contribute non-trivially to the total rate or total population of the black holes, binary black holes that LIGO and Virgo are observing.
Okay, thank you.
Gopal?
Hi, Ilya. Very nice talk. This is about 190521, the MBH. There have been already suggestion that they can actually come from highly eccentric binary, In fact, you can actually argue that they can even come from head-on collision. So such signals will be very difficult to, pinpoint, at least in this era, but maybe eventually. So you might have lost bet in other one too, if that is the case.
Hi, Gopu, you're absolutely right. But I think, so this is my personal take on this. I'm actually not convinced either by the argument made in the initial LIGO-Virgo discovery papers that there was significant precession, or by the arguments which I'm familiar with that this is consistent, that this source is eccentric. I agree that it's consistent with having a significant eccentricity. It's also consistent with being a circular source, but with a significant amount of precession, or precessing a spin that's in the orbital plane. But I think really what, let's look at the signal, right? The main story here is we see this ring down and we don't see much before that. So the main story is somehow this ring down is turning on quite abruptly. Normally, you might expect that there should be a more gradual turn on with a merger signal preceding this ring down signal. And I think really what all of these models are telling us is that there's something fishy going on here. The turn on is a little bit too more abrupt than one would expect, but I don't think we necessarily know yet what is causing that abrupt turn on. A precession is a plausible explanation. Eccentricity, or even a head-on collision, as you say, is a plausible explanation. And maybe there are some other explanations we could come up with here. Unfortunately, with just a few cycles, it's very hard to tell exactly what's going on. So I think we may have to wait for a little bit longer to figure out which of those explanations is the right one for the sudden turn on or relatively abrupt turn on of the amplitude in the signal.
It can be even Brill zoom at the last phase or something. That is also technically possible. I've been trying to see whether it's possible or not. So yeah.
Sorry, actually, I didn't catch the last thing you said.
That's a Brill zoom orbit people are talking about. You don't need to bring high masses. I mean, you may have to bring higher masses, but it is in principle possible, but it's complicated. So
I think that's a great explanation. I like this very much. Well, absolutely. So I agree. Indeed, as you say, there at this point there are multiple possible explanations. I've actually toyed around with the idea that it could be some kind of a in principle at least. I'm not saying that I believe this, but it could be some kind of a bumpy black hole, or a let's say non-classical GR object. And again, that could lead to some deviations in the latent spiral and merger that might lead to a rapid turn on. So I'm fully on board with the fact that there could be at this stage multiple alternative explanations. I like the Zoom World one. Thank you.
Thank you. Thank you very much for a very nice talk too. So again, thanks.
Thank you.
Jagadeep, next question.
Yeah, I have a very naive question. If you look at formation of neutron stars, they invariably end up having a big spin because as the core contracts, if you think about conservation of angular momentum, the core spins.
Jagadeep, can you speak a little louder?
Yeah, sure. Now is it better?
Yes.
Yes, thank you.
Okay, so I was just saying that if you look at neutron star formation, you expect them to be spinning very fast because of conservation of angular momentum. So I am asking a naive question about black holes. The same way, if you think about a neutron star and contracting it even further to a black holes, why do you expect any black hole to have low spin? Shouldn't they all be having extremely high spin?
So that's a very good point. So well, so with neutron stars, as you probably know, they don't necessarily all have very high spins even at birth. Of course, we don't know exactly what the birth spins of magnetars are, but the spins aren't necessarily as high as maybe conceivably as maybe possible. And there are lots of discussions about why that happens. It could have something to do with the gravity modes in the stars, for example, transporting angular momentum at moments just prior to collapse. But in the case of black holes, actually, the spins that we're talking about, when we talk about high spin, I should have been more careful. So what I mean by high spin is spin near the allowed maximum. So there is this parameter chi, which describes the maximum allowed spin for a Kerr black hole, and it essentially, you can think of this as having it's in dimensionless units having a spin angular momentum that's equal to the mass squared. So what this means is, another way of thinking about this is that okay, if you could talk about such things as binding energies and rotational kinetic energies for black holes, it would be kind of like saying that this is an equilibrium between, roughly speaking, between the kinetic energy and the gravitational binding energy of the black hole, rotational kinetic energy. So these really are extremely rapidly spinning objects. For comparison, the fastest spinning neutron star that we know of in a double pulsar, the pulsar in GEO 737, only has a dimensional spin parameter of about 0.04. And it actually is not that easy to have this very high spin. While it is possible, certainly for a Wolf-Rayet star, for example, to have spins this high, stars tend to spin themselves down by losing mass through winds, and stars in binaries can also lose a lot of angular momentum when they eject their envelope, or when they lose their envelope, whether it's stable or unstable, when the envelope is stripped off by the companion. And so it's actually not that easy to have a star be sufficiently rapidly spinning. One of the ways to do that might be through tides, where tides in a sufficiently compact binary can spin the black hole progenitors up. And this is one of the ways that we and other people have argued that at least some black holes in binaries might be rapidly spinning. They may also be true for chemically homogeneously evolving stars. But the general story is that it's actually not all that easy to get a particularly rapidly spinning black hole.
Thank you.
Saurav, just a follow-up question. I'm sorry. Can I?
Sure, please.
Okay, thank you. So this is about, suppose you have figured out, we discovered a sub-millisecond pulsar. Will that have any implication for, some of your scenarios?
Ooh, that would be very interesting. So I think, well, so I...
Will you be happy?
I'll be very happy. I will definitely be happy. Look, I'll be happy with any exciting discovery because, as a theorist, it gives me something to think about. So that's always fun. So look, the simple story is we actually don't know why there seems to be an upper limit on the spin of neutron stars and why it falls in the place where it does, right? The fastest spinning neutron stars we know of have a spin frequency of about, 700 hertz. And that's actually below the maximal limits that can be theoretically placed on neutron star spins. So in fact, it's an open question, what does it? People used to think that it might even be gravitational waves that spin down neutron stars that are spinning too quickly, because if you imagine that a neutron star is developing some kind of an asymmetry or some kind of oscillatory modes, especially as a result of accretion, that certainly seems plausible, then maybe that's what's causing neutron star to spin down and stay below this limit. But one of the interesting questions is, what actually is it that allows a neutron star to be recycled, right? Because when we talk about millisecond pulsars, we're not actually talking about the burst spin of neutron stars. We're talking about recycled neutron stars. So we're talking about neutron stars that, I'm sorry?
Yeah, right, precisely.
Right. We're talking about recycled neutron stars, which means that somehow by accreting mass onto a neutron star, you manage to spin it up again. But in fact, if you think about a neutron star with a strong magnetic field, accreting mass onto it should actually spin it down, not spin it up. Because you have this propeller mode accretion, as it's called, but basically the way to think about this is the coupling between the accreting flow and the neutron star's magnetic field sort of happens at something like the Alfvén radius, sort of at the edges of the neutron star's magnetosphere, which is pretty far away, where the Keplerian angular velocity is actually quite low. So the neutron star, an accreting neutron star, ends up going to equilibrium with the angular frequency or Keplerian angular velocity at its magnetosphere radius, which means it actually ends up being a very slow spinner. And we know this happens, by the way, because, for example, in BX3 binaries, we see that there is a strong connection between the orbital period and the spin period. So, this is observationally the case. This is really what's going on. So if that's the case, how do we ever overcome the magnetic field? And one possibility, so people often talk about burying the magnetic field, but one possibility is that it's actually not that easy to stick the magnetic field back inside the neutron star. One possibility is, in fact, that what accretion does is it doesn't bury the magnetic field. It's actually that when you slow down the neutron star spin, you pull the magnetic field out rather than burying it. You pull it out from the neutron star core into the crust, which is no longer superconducting, and where you therefore have ohmic resistance and can dissipate the magnetic field. So over time, you dissipate the magnetic field. And the question is, how efficiently do you dissipate it, how long it takes, and whether then you have subsequent accretion that can spin the neutron star back up again without giving it a magnetic field. And so I think detecting, whether or not we detect a sub-millisecond pulsar, I think one of the very interesting questions is, what can we learn about the actual process of how neutron stars get recycled and how they accrete mass? And I think that's interesting both in the detailed physics of neutron stars and also on, for example, understanding exactly how mass accretion proceeds onto a neutron star in a binary.
Thank
you. Shubham Bharadwaj.
Yes, sir. Hello.
Hello.
Yes, sir. Can you hear me?
I can.
Yeah. Thank you for the nice talk, sir. So my question is that, is there any possibility of sense of multiple GW, like from two different sources, GW is propagating and they can interface?
Okay, so you're asking whether there can be where the gravitational waves can interfere with each other?
Yes, sir.
Okay, so in general, because general relativity, of course, is a nonlinear theory, but because gravitational waves are such weak perturbations, by the time that they are anywhere close to our detectors, we can think of them as being very much in the linear regime. And so they do linearly interfere and they do superpose on top of each other. And it's absolutely the case that we can have multiple gravitational wave sources. In fact, we do have multiple gravitational wave sources acting at any one time. And so there is a superposition of gravitational waves. The question is it likely to be detectable? There are searches for stochastic backgrounds, for example. So this is a case where you may have lots of gravitational wave sources at the same time, and those sources are interfering with each other. So you're sort of awash in this background of gravitational waves coming from multiple directions, incoherently interfering. And can you detect this sort of gravitational wave noise, essentially? And there are efforts to do this. There are efforts to do this with ground-based detectors like LIGO, but perhaps even more relevantly, there are efforts to do this with pulsar timing arrays. So the idea behind pulsar timing arrays is to use a detector that's automatically built by nature. So as you know, pulsars are, at least some pulsars can be very precisely timed, but when the radio signal from a pulsar is moving from the pulsar towards the Earth, you can think of it as surfing on a background of gravitational waves. The gravitational waves have nothing to do with the pulsar. They have, in this case, we're talking about very low frequency gravitational waves, so they're probably due to supermassive black holes that are spiraling together because their host galaxies merged, and now the black holes are in the process of merging. And there may be multiple such sources going on at the same time because these are very slow processes. taking millions of years. And we see one galaxy doing this at the redshift of 1, another galaxy doing it at the redshift of 0.5 in the opposite direction, and so on. And now you might be in a situation where there are multiple such gravitational waves, gravitational wave signals, and the pulsar timing arrays, which are timing the photons coming from the pulsars and looking for residuals, meaning any deviations from the expected predicted arrival time of the photons due to the delays imposed by gravitational waves. Those might, for example, be sensitive to a stochastic background of gravitational wave signals.
So if we could able to detect, then how could we differentiate between, like, from what sources it has like formed the interference pattern?
So in the case of stochastic background, you won't be able to. All you can tell is the overall amplitude and the slope of the background, meaning, okay, you can do basically a spectral energy density estimate, and that's telling you something about the kinds of sources that are causing it, if you can do that estimate. But sometimes you can also, if there are bright enough individual sources, it's okay to have multiple sources at the same time, right? If the sources are separated in location, you can go and see multiple stars in the sky with a telescope. You can do the same thing with gravitational waves, or if they're separated in frequency. So you may have two sources at the same time, but if one of them is at a different frequency, like if you look, for example, at this plot, you see on the bottom are time frequency spectrograms. You can imagine having two sources that overlap in time, but that are at different frequencies at the same moment in time. Those would be quite easy to distinguish. And LISA, a planned mission to detect gravitational waves from an antenna in space, LISA stands for Laser Interferometer Space Antenna, that is going to be, among other things, sensitive to tens of thousands of double white dwarfs in the galaxy, emitting gravitational waves all at the same time. But because they are separated in frequency and separated in location, it's going to be able to observe them and distinguish them.
Okay. Thank you, sir. Thank you for the explanation and for a nice talk.
Thank you.
Ilya, we are almost running out of time. I have maybe time for one very quick question, and I will ask that. So I was very interested in some of your microlensing results, and in some other cases, you have black holes that are in the lower mass gap between neutron star and black holes. So is this, for example, we know there are two different ways it can come, prescription wise. There is this so-called delayed prescription that can happily produce black holes, and there is no mass gap there. And there is also, even if you have a mass gap, you can create black holes that reside in the mass gap through accretion-induced collapse. So I was wondering, the ones that you see, are they AICs, or is this prescription-based, no mass gap type population?
So it's hard to convincingly say which it is. I think I would err on the side of the fact that this doesn't require accretion-induced collapse, because I think those would be too rare. If we look at the relative ratio of few solar mass black holes to neutron stars, for example, among microlensing events, I don't think that it's realistic to have enough accretion-induced collapse events. I also think it's hard to imagine, for example, in the case of the LIGO event, where there was a 23 solar mass black hole merging with a 2.6 solar mass compact object. It's hard to imagine how there could have been an accretion-induced collapse, at least if it was a binary to begin with. Now, of course, dynamical scenarios might allow that for that to be an accretion-induced collapse event, but still, I think that okay, one of the things we will be able to test when we have a bigger population, but I think they'll be too rare to explain the relative frequency, at least according to microlensing observations, of lower mass gap events.
Okay, I agree with you.
By the way, the same also goes, I mean, there's at least one more thing that can do it, right? We know when two neutron stars merge, they form a compact object that's, right around, can be right around 2.6 solar masses, right? If we take, two 1.4 solar mass neutron stars, that's what you will get. Okay, whether you argue it's a neutron star or black hole is a separate story, but you'll get something in that mass gap. But again, we don't have enough binary neutron star mergers, I think, to explain the relative frequency of such events.
Thanks, Ilya. Let's thank Ilya again for the excellent talk and discussions. We have to end the session now. There are other time constraints. Let's thank Ilya once more. And hopefully he will visit us when everything becomes normal. Thanks, Ilya.
Thank you very much again for your patience and for the great questions. And it was a great pleasure. Thanks.
Bye.
Take care.
Bye.
Bye. Bye.